let's continue to another part where we are going to take a look on the particle in a uniform circular motion. Alright, let's say we have a car as our model particle here. Okay, we also experience this, right? Whenever we enter a roundabout, okay, so we are moving, okay, along circular path, almost a circular path, takkan, depending on which exit you're going to take, isn't it? Let's say this car is moving with a constant velocity, with constant magnitude of the velocity or constant v value, all right, tangential to at any position. So at this moment, okay, this car having r position, r initial, let's say. After certain time, let's say the car already here, so now you have another r here, which is r final. So here it is covering initial angle, and here for this position now, okay, is going to have another position angle. So in simple, you're going to have two new information of position. Based on our experience, if we take a roundabout and you are speeding up, you're going to have difficulty in handling the steering, isn't it? You're going to experience like you're going to move away from the roundabout, going to exit the roundabout. Okay, so you need to balance, right? Okay, and sometimes you are driving, you're going to feel like you're going to fall into the center of the circle as well, right? Sometimes you have a feeling that you're going to move away from the roundabout. So those feeling actually involving some kind of force and also acceleration. We're going to take a look on this in detail. So now, let's say initially, okay, the object is at point A. So at this instant, the object has r initial, okay, position vector. At this instant, the object is having a velocity initial, okay, in this direction, okay. And then when it reach point B, now, okay, it has r final position with v final of velocity in this direction. So when we talk about how to figure out the delta v, of course, not to forget that we have to have delta r over delta t. So what is the delta r? Is the change of the r final to the r initial in comparison, okay, from position A to position B. Okay, so if you see here, okay, in technical method, okay, it is a triangle, right? All right, this triangle, okay, can be manifest or transform into this kind of triangle, right, with the condition that the angle covered here is the same with this angle. Okay, so we have v initial, okay, let's say this is your v initial, right? Okay, just imagine we transfer it here. Okay, so this is your v initial, and then this is your v final. Your v final, okay, you transfer it here, you transfer it here. Okay, so this is true as long as the angle here is the same with this angle, right? So what is the purpose actually when we do this? We are actually trying to figure out in terms of vector drawing or technique, okay, to figure out the delta v, since our interest is about delta v, to figure out the A, right? So you have v initial in this direction and v final to this direction. What does that mean by delta v? Delta v is defined as v final minus v initial. It's also the same meaning of v final plus negative of v initial, isn't it? So means that we can have negative v initial. So initially you have V initial in this direction. Now to have negative V initial, you just turn the direction oppositely. Okay, completely opposite. Remain the length of the arrow but in opposite direction. So, okay, you have your V initial in this direction now. Instead of, okay, within this direction, okay, now your V initial in this direction. So, initially the object having V initial. So, now it's already negative V initial. Then, another vector that the object has is V final. So from tail of the V initial, negative V initial, to the tip of the second vector, which is the V final, that will be the resultant, which is your delta V. Okay, by definition, is equivalent to V final minus V initial. Right? Why are we concerning about this? Why we want to take a look on this matter? Because actually the A is defined as delta V over delta T. So the A average involved here is delta V equivalent to over delta T. So what happened here? Okay, how come this is true? This is actually how to transfer this triangle to this triangle. It's only valid whenever you have this ratio. When the angle is the same, A average is equivalent delta V over delta T. What is delta V over delta T? The delta V itself from here. Okay, the delta V itself from here. Okay, to have a delta V over V equivalent to delta R over R. So to have only delta V is equivalent to delta R over R times with V. So this is what is happening here in this. Right? So it's just that you divide this by T. So also you have T here. Okay, why are you interested to divide this with T? Because you are figuring out A average. Okay, that is how to get the formula. So we are still referring to the same diagram actually, but now from the part that we have previously, where the A average, okay, is equivalent to delta V over delta T, the idea. And what is our delta V is V delta R, okay, over R delta T. So if we refer to this, okay, this is actually V, isn't it? This one is V because it's change in position over time. So the A average here is actually equivalent to, okay, V squared over R. Let's imagine, okay, the angle here decrease, okay, approaching 0, become very small. Okay, so the arrow here, okay, become nearer to point A. Okay, so what will happen? Okay, the angle here going to be very small, right? So the A average going to be A instantaneous, isn't it? Because, okay, now whenever our R final, just here, this is our R final, let's say. So the angle here, very small, very narrow. This is our angle right now, delta theta. Okay, so the V final is here. Almost the same, right? So almost the same. So means that we can have, okay, for this point is almost the A average, almost the same to the A instantaneous. Condition, the angle is very small, representing the time also approaching 0. So now the A that we experience when this situation happen is known as centripetal acceleration. So centripetal acceleration in simple is the A that cause us or have a feeling right that we're going to fall to the center of a circle when we have circular motion or circular path taken. Okay, that is the one that we feel, we have a feeling like we are going to fall down into the center, to the center of the circle. Alright, so talking about circular motion, of course we are going to have period of it, time of it, the speed. Instead of having changes in speed and also direction, okay, we can have also another term, right, in term of angular, we call it, right, particle in uniform circular motion. So let's have a picture here. Take a look on this picture. Okay, an object is moving within a circular path, okay, having r radius at any time from the center of the circle. The object has the v velocity at this instant and also experience centripetal acceleration, the A that causing us have a feeling like we are going to fall down into the center of the circle. Okay, let's say now the velocity of the object is constant, right? If the velocity is constant, okay, the magnitude stay the same, but then the direction of the v keep on changing. Why is it so? Let's say the object now reach this point. Okay, what is the velocity of the object? It's going to be tangent to the point. So this is the v of the object. What about if it is already reached here? Tangent to the position of it here. So if you see here, the direction of the v keep on changing even though the magnitude of it remain the same. So the direction here keep on changing, bear in mind, even though the magnitude stay the same. So talking about the magnitude itself, okay, we can have another approach when we have a circular motion, okay, because to complete one circular path, okay, the distance travel is the circumference of the circle, right? And the time taken to complete one circular path is a period, because this is a repeated motion, right? So speed of the object is defined as equivalent to distance travel. This is actually coming from speed equivalent to distance travel over the time taken to travel that distance. So distance travel is the circumference over the time taken is a period. So a period for this object going to be, rearrange the equation, 2 pi r over v. And this is at this particular and this particular point and this particular point. In general, we can see that the object having circular motion, isn't it? Circular motion, where the speed in terms of circular motion also have another name of it, which is angular speed, okay, or angular frequency. Okay, so angular speed or angular frequency is symbolized as this, omega. Okay, so at any instant, in general, okay, the object is rotating, okay, about a fixed point, which is the center of the circle, with circular speed or angular speed of omega. For this case, it's counterclockwise direction, which is equivalent to or defined as, okay, omega. Actually, this is based on definition of omega is how many delta theta covered, okay, or experienced by the object over the time taken of the object to have that delta theta to be covered or done. Alright, so the delta theta for one circle is 2 pi, and time taken to have one complete circle is period. Okay, that is why omega is equivalent to 2 pi over capital T, or period. Right, and from here, okay, we have a formula of the period. So substitute to this, you will get this pattern. And finally, you're going to simplify the formula. Okay, is equivalent to V over R. Okay, so V is equivalent to R omega. This is the one that important. Right. So what does that mean? What is V? What is omega? V is a linear speed. Okay. Whenever you move in, you are driving a car and taking a roundabout. Are you rotating your steering? Obviously no, right? Okay, you're going to turn your steering slightly, a bit by a bit, isn't it? Okay, in taking the roundabout. So this is what we call it. This is your tangential speed. Okay, why is it tangential? Because it tangent to the point or position. Okay, or speed, simply known as speed. Okay, this speed is linear. Okay, how about this speed? This is angular or circular. Okay, where we define it as it move, okay, within a circle like this, right? So the unit of this one, for according to this formula, the unit going to be radian per second. Okay, and then this one is meter per second. So by taking into account the omega just now, we can have a new form of your AC, which is V square over R. Okay, so now substitute the V into this as this one. So R omega, everything squared over R. So you have R omega squared because cancel out with this one. Okay, so the most important part here is centripetal acceleration equivalent to R omega squared. What is the unit of your AC? Meter per second squared. Right. So in general, for an object or particle moving within a circular path or experiencing circular motion, it also now has the omega, angular velocity or angular speed. And also known as angular frequency, another name for omega. Okay, angular frequency, because it tells us or give information of how many angle within a unit time. That is why we call it frequency, angular frequency. How frequent the object going to revolve over unit time. Okay, so now the AC is equivalent to V square over R. And we know that the total time taken to move within circular path is the distance traveled, the circumference of the circle over the velocity. Okay, the tangential velocity or speed. We are talking about time, no different in terms of that. And the angular speed or angular velocity, if you're talking about the direction, angular velocity, if you're talking about only magnitude, then it's known as angular speed, is equivalent to 2 pi over t, right? So 1 over t, if you still remember, is actually 1 over t or 1 over period is frequency, right? Because of this, we may now rewrite this equation into 2 pi f, another form. Alright, what is the unit of your omega here? It's radian per second. What about F? Hertz or per second. What about A? Meter per second squared. What about V? Meter per second. What about R? Meter. So every single thing, make sure is in SI unit. Right, example 4.6, the centripetal acceleration of the Earth. Okay, what is the centripetal acceleration of the Earth as it moves in its orbit around the Sun? Okay, so AC equivalent to V square over R. What is our V? V is defined as distance traveled over the time taken. We assume that, that the orbit is a circular pattern. Okay, so actually in real world it's not like the orbit is elliptical orbit, but then as of now we assume that it is circle, right, over the time taken to have a simplicity. Okay, over the r, so squared everything here, you have 4 pi squared r over t squared, and then you're going to substitute the distance, okay, or radius from earth to the sun. Okay, this must be taken from your textbook. Okay, you have to figure out from table or appendix, please refer. Over the time taken, 1 year, right, we orbit the sun a complete circular path within a year. So within a year, how many seconds? Convert it, right? And then you will get this as our centripetal acceleration. So this is what we experience when we are orbiting the sun. Okay, very small amount, right? That is why we didn't notice actually. B, what is the angular speed of the earth in its orbit around the sun? So angular speed, no need to determine whether it's clockwise or counterclockwise. Okay, so omega is distance travel for one circle is 2 pi. Time taken is 1 year for the earth to circle or orbit the sun. So you get this answer. So this is supposed to be radian per second. Let me amend it. Okay, it's supposed to be radian per second. Radian is sometimes some of the book didn't write down as this one. Radian is actually ratio of sides of triangle, right? Same goes to the degree, isn't it? Because degree also ratio of sides of triangle. So it's not a real, or we can say it dimensionless. Tangential and radial acceleration. Okay, so at any instance, okay, let's say we take even more general information or motion of an object. Okay, let's say an object is moving within this path. Okay, so this is the path of the object or particle that we're going to consider, the black dash line here. So at this position, okay, it has information of the A tangential to this, because this is actually a part of this circle, right? And it has A that directed always pointed to the center of this circle. Okay, so now this A is symbolized as AR. Okay, stand for radial acceleration. Alright, and here is AT, stand for tangential acceleration. At any instant, the object is actually experiencing A as the resultant, where it is actually a combination of AT and AR as written here. Okay, so we know that, okay, AT is equivalent to dv over dt. What does that mean? It's change in the velocity to the respect of time. Okay, so change of what? Why is it modulus here? Change of the magnitude of your velocity that producing or causing tangential acceleration to be exist. Okay, so the existence of the AT is due to the change of the velocity, change of the magnitude of your velocity. If let's say the object is moving with constant velocity, alright, still we are going to have AR or AC previously in our previous lesson. Here, okay, the AC pointed to the center of a circle, okay, which is equivalent to V square over R, centripetal acceleration. Why is this happening even though the V is constant in terms of magnitude? Because the direction keep on changing. Okay, always tangent to the point, tangent to the point. So now Okay, changes of magnitude within the tangential velocity causing the tangential acceleration exists, and changes of the direction of the v. Okay, if let's say there is no change in magnitude, but then still we're going to have change in direction, because at any instant the v is always tangent to the point, let's say, okay, for a circular path. Okay, so the v, even though the v could not be changed in the magnitude, it always change in terms of direction. This is a recall from previous slide, right? So with that, okay, changes of the direction within the velocity producing the centripetal acceleration, or also known as radial acceleration. Okay, but then here you have negative sign. Previously you don't see the negative sign here. What does that mean by negative sign? The radial or centripetal acceleration always towards the center of the circle, which is in opposite to the r. R is always away from the center of the circle. Okay, let's say the object is at this point. The r will be in this manner. The r initial, let's say. Now the object move to the second. This is initial point, this is final point. Now the object has r final. You see, the direction of the r always away from the center of the circle. Whereas, okay, the direction of the ar always to the center of the circle, right? Always to the center of the circle. That is why it has negative sign, right? So back to the magnitude of it, okay, it's equivalent to v squared over r. Okay, so at any instant, okay, we as the object experience two kind of at and ar. Therefore, to have the magnitude of the a solid or resultant that the object experience, you have to use Pythagoras like this. Then you may also determine the direction of your a by calculating angle. Okay, if let's say the question asking for a direction, so you're going to finish it with this arctangent of, okay, because they are perpendicular to each other. If madam is writing this angle to the reference, so tangent, what does that mean? AR over AT for this case particularly. So it depends on which angle. As long as you know what are you doing, whether it's tangent or sin or cos, doesn't matter. So example 4.7, over the rise, a car leaves a stop sign and has a constant acceleration of 0.3 meter per second squared parallel to the roadway. The car passes over a rise in the roadway such that the top of the rise is shaped like an arc of a circle of radius 500 meter. At the moment the car is at the top of the rise, the velocity vector is horizontal and has a magnitude of 6 meter per second. What are the magnitude and direction of the total acceleration vector for the car at this instant? So at this instant, the car has a v tangential of 6, and it also has tangential acceleration 0.3. Okay, constant acceleration of the car parallel to the roadway. When it is parallel to the roadway, this is the roadway, parallel to the roadway. Okay, so means that it is AT, right? So it's AT, which is towards the center. If it is towards the center of the circle, then it's AC or AR. Okay, now AR is equivalent to negative V squared over R. Okay, so you have here AR also equivalent to AC, remember? Alright, then substitute the information of your V and your R, you've got this answer. To have the magnitude of your A for your car, you have to use direct Pythagoras because at any instant is actually combination between AR and AT. So you have this information. How to visualize this? This is actually to similar or manifest in terms of this diagram, where you have tangential acceleration and define the angle covered, the solid A, the net A, the resultant A experienced by the car, and then the AR always to the center of the circle. And then next one, the angle here, the phi, is arctangent of AR over AT. Why is it AR over AT? Why not AT over AR? Is because you are using tangent. Okay, tangent is opposite over adjacent. Right. So you get the answer of negative 15 degree. In terms of meaning, okay, what does that mean? Okay, if this is your car, okay, this is the path taken, right? And your car is having AT here and AR here, okay? At this instant, you have a combination of them. This is your solid A and this is your angle phi. This is the meaning, okay, of this drawing. Right. That's all for chapter 4. Thank you very much for watching. Any part is not clear to you, do ask question to me. That's all. Assalamualaikum.